Hello, and welcome to the 8th issue in the FastScan market campaign. This is Johannes Kind, and I am happy to send you the special treat in time for the holidays. A Dimension FastScan investigation of chocolate. Chocolate consumption as a confection is widespread in most developed countries. Does chocolate simply have exceptional orosensory properties, or are its effects more complex? Bruinsma and Taran explore this question in their 1999 review paper, Chocolate, Food or Drug? From a colloidal perspective, chocolate consists of micron-scale particulates, sugar crystals, cocoa particles, and milk powder, dispersed within a solid liquid fat phase, consisting primarily of cocoa butter. While responsible for the snap, gloss, and sharp melting profile of chocolate at body temperature, cocoa butter is also the culprit in fat bloom, a defect that afflicts all chocolates. On the right we see data from a 2002 AFM study of chocolate bloom after thermal cycling by Hodge and Rousseau. When cycled thermally, more continuous phase material of cocoa butter is found on the surface and is available for fat crystallization, the infamous bloom. Imaging the surface of chocolate can be rewarding in a demo. You can image one piece while sharing the rest with the customer. Sample prep. None really required. Break off a piece of chocolate, make sure to image one of the higher areas, for example the raised frame on this Lindt chocolate. Try to image an untouched area. For optimal stability, you can mount the chocolate piece on a glass slide. Turn on the hot plate until hot to the touch. Put the piece of chocolate on a glass slide. Put on the hot plate for 5 seconds. Immediately put in the freezer for 30 seconds. Done. The chocolate top or molded surface was relatively smooth here, tens of nanometers locally, and less than 2 microns over the full scan size of 30 microns. The wrapper materials are best imaged on double-sided sticky tape, on the stage or on another glass slide. Just cover with a clean piece of paper to apply pressure with your finger. Atomic force microscopy provides detailed insight into consumables' nanoscale surface morphology and interaction of, for example, food, primary and secondary packaging. 30 by 30 micron 16 megapixel AFM survey scans were obtained in tapping mode at 1.6 MHz tapping frequency of chocolate, aluminum and paper wrapper. Each high-resolution scan was taken in under 10 minutes on the Dimension FastScan, rather than, for example, 3 hours on a standard AFM. Here we see the results. The 3 images are already 2x zoom-ins of the original 30 micron 16 megapixel images. These are phase images of the chocolate surface, the aluminum foil and any material that may cover it, and of the paper wrapper. Each 16 megapixel survey was taken in under 10 minutes. Each has a lot of long-range heterogeneity that can only be seen in a large scan. Now we will zoom into the blue boxes and see that each also has enough nanoscale detail to require the high resolution. Here are the 3 data zooms from the blue boxes in the previous slide. The large scans gave us the context to know we are looking at representative morphologies. These zoom-ins now give us the detail for some interpretation. Since these are phase images, the colors represent variations in stiffness or adhesion. The chocolate has a finely modeled domain structure as described in the literature for fresh chocolate, with defined particulates and a darker colored continuous phase which may be fat. On a comparable scale, the aluminum wrapper surface interestingly shows 3 distinct phase responses and associated morphologies. On the aluminum background, with the least phase shift, are small rod-like structures of softer or more dissipative material, and 1 to 2 micron sized spherical objects with more sharp-edged leaf-like structures in their periphery. A plausible interpretation would be that the spherical structure is a fat droplet or cocoa dust particle, for example deposited during production, or by sublimation within the package. The radiating, sharp-edged leaves may show some of this material in the process of recrystallization. What is interesting is that these can be found on the aluminum but not on the chocolate itself. It could be interesting with regard to the aluminum foil's role as a protective wrapper if aluminum surface promotes fat crystallization. The image of the paper outer wrapper shows two morphologies, with different phase contrast. The expected paper fiber structures, as well as aggregates of 25 to 30 nanometer particles between the fibers, which may be the dye particles causing the red wrapper color, and or be a filler that contributes to the paper's gloss and texture. Now we are coming to the piece of data that gave this project the title: High-Speed Nanomechanical Mapping of the Chocolate Melting Transition. This movie by Hartmut Stadler of a roughly micron-sized area was taken on a chocolate film spread out on a cover glass for measurement on the Dimension heater cooler. The imaging mode was PF-QNM at 8.8 lines per second. The FastScan specification says that QNM does not currently provide information faster than a standard system, and this is still mostly true. What happens when running at 8.8 Hz and 256 pixels per line is that the QNM data is low resolution in the horizontal direction, with each material value spanning multiple pixels. However, the topography information has the full pixel-to-pixel resolution. This can be a fair trade-off when the topography provides good feature definition and the lower resolution QNM data provides the features properties. To visualize, first the QNM data was blurred in the Y direction to remove the distracting dash appearance of the material channel. Then, in nanoscope analysis, the topography data was displayed in 3D, with the material properties overlaid as a color map. In the movie, the change of material deformability while the chocolate approaches its sharp melting point around 30 degrees C, which, importantly, is above normal room temperature of about 21 degrees C, but below body temperature of 37 degrees C. First, the softening effect can be seen at two structures coming from the top and bottom, later from the right. Each frame in the movie was recorded in 30 seconds. Thermal equilibration times on the micron scale can be expected to be in the millisecond range or below. Therefore, the propagation effects in the consecutive movie frames cannot be heat propagation. Rather, they ought to be associated with material transport of some sort. The surface topography is fairly stable throughout the movie. Therefore, inner material transport effects, for example increased solubility or miscibility, could be the cause. The fat phase separation seen in the literature after thermal cycling is more likely to occur during a cooling cycle. The technique of combining high-resolution, high-speed topography data with simultaneous, slightly lower resolution QNM data could be interesting for the study of many dynamic processes. Conclusions: 30 micron 16 megapixel overview scans were performed on the surface of chocolate and its wrapper layers. Review of the high-resolution phase data identified the representative nanostructures of each surface type. The most remarkable observation here were 1 to 2 micron domains of soft material on the aluminum, surrounded by structures of crystalline appearance not present on the chocolate surface. A chocolate film on glass was imaged in PF-QNM while heating, at a rate of 2 frames per minute. Propagation of material property changes can be seen at rates on the order of 100 nanometers per minute, orders of magnitude slower than the thermal equilibration times, but consistent with material transport, for example surface energy-driven wicking or diffusion. The constant topography speaks for diffusion effects within the bulk material. This work was enabled by the Dimension FastScan's unique combination of speed, nanomechanical property mapping, large real-life sample capacity, and capacity for thermal control. We hope that you will enjoy some good chocolate FastScan demos with your customers, including all the beneficial side effects discussed by Bruinsma and Taran. Stay tuned for the next piece, which will take us into screening applications with FastScan. Happy holidays!